The last type of transforms that we're going to look at are between our cylindrical and spherical coordinate systems. I've copied here the figure that we used in our previous video where we're looking at transforming between Cartesian and spherical coordinates. So the same sort of geometry and trig is going to apply, except now instead of relating x, y, and z, we're now looking at rho, phi, and z. And of course we're relating that ultimately to our r, theta, and phi. So of course we can see an overlap there with our phi being included in both, so that's going to make at least one of our sort of equations a little bit easier. Okay, so let's start by writing our point-to-point transformations. And so like with the previous two videos, I'm not going to go into all the details of the trig behind this, but you can kind of use this figure to figure it out yourself. But if you have any questions, definitely let me know and I'll be happy to go into more detail. So our point-to-point transformations, again, we're taking a point that's defined with cylindrical coordinates and defining it with spherical coordinates or vice versa. So let's start by saying we have our cylindrical coordinate and we want it in spherical coordinates. So using trig in the figure above, we can say that r is equal to the square root of rho squared plus z squared. Our theta is equal to the inverse tangent of rho divided by z, and our phi is of course just equal to phi. And we notice with these first two terms that these are sort of just combining equations that we had in the previous two videos. So we're essentially just simplifying. We had x squared plus y squared, and we can substitute that with our rho squared here, and here we're using sort of that relationship between x, y, and rho. So this is if we had cylindrical and we wanted to go to spherical. But what if we wanted to go the other way? So again, using the figure above and trig, we can say that rho is equal to r times sine of theta. Our z is equal to r times cosine of theta. And again, our phi is just equal to phi. So this is if we were going from spherical to cylindrical. So that is for our point-to-point. Now let's look at our vector-to-vector transformations. And so these sort of, the derivation for this is not shown explicitly in the textbook since this is a problem in the end of chapter problem. So if you do have questions about the details for the second part, these vector-to-vector transformations, let me know and I can share with you sort of the details of this. But ultimately, again, you're not going to need to memorize how to derive this or anything like that, just so long as you can reference the equations and use them appropriately. So let's say we're looking for our spherical coordinate components, so our AR, our A theta, and our A phi. So we're going to have some 3 by 3 matrix, which is going to be multiplied by our cylindrical components. So our A rho, our A phi, and our A z. So now of course we know we have the same phi component, so for our third row we're going to have 0, 1, 0, and essentially that's just saying A phi is equal to A phi. For our first row we're going to have sine of theta, 0, and cosine of theta. For our second row we have cosine of theta, 0, and negative sine of theta. And again, this all just comes from relating unit vectors of one coordinate system to unit vectors of the other using trig and sort of analyzing that. Okay, so this is going from cylindrical to spherical. But like we've seen in the previous two videos, if we look closely, we notice that we have theta, 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 theta. So we have cosine theta and sine of theta that we need to deal with. But if we really only have cylindrical, everything should be in terms of rho, phi, and z. So how do we deal with that? Well, we can use essentially the same equations we had in the previous video, but now we're going to define it using rho instead of x and y. So we can say cosine of theta is equal to z divided by the square root, and now we're going to have rho squared plus z squared. So again, this is essentially still r, but instead of defining this denominator which is equal to r in terms of x, y, and z, we have it in terms of rho and z. Similarly, we can say sine of theta is equal to rho divided by square root of rho squared plus z squared. Again, same equation as in the previous video, we're just using rho instead of x and y. Okay, so then finally, if we want to go the other direction, so let's say we want to find our cylindrical components, a rho, a phi, and a z, given our spherical components, how can we do that? So without going through the derivation, we can just write the results. We're of course going to depend on AR, A theta, and A phi, and we should be able to do the second row pretty easily. We know that's going to be 0, 0, 1 because phi is equal to phi. For our first row, then we have sine of theta in our first entry, cosine theta in the second column, and 0. And then for our second, or rather our third row, we have cosine theta, negative sine theta, and 0. And so this is how we would go from spherical to cylindrical vector. So that's it for the different types of transformations we can do between the various coordinate systems. What we're going to do in the following videos is we're going to take a look at a couple examples and get some practice using all of these different equations.